Okay, welcome to the second part of today's math camp. We're going to start where we left off, which is, I think is 3, right? But before we do 3, let me just get a recap for number 2, which talked about the interior point. So basically, when there's a metric space X and when there's a subset A, we say a point X in A to be an interior point of A, only if when we can find some sort of small open ball that it can go inside the set A. So I already draw some graph to show this. For example, there's a metric space and there's some subset. We say this point is the interior point of A if there is some epsilon we can find such that there's a ball like this so that the ball goes inside the A, then we say this point is an interior point. In this case, so that definition goes with this number 3, which is connected with when we say A is an interior set. We can say A is an interior set, but I think it's more normal notation for this is actually we call A to be open set. So we say A is open if there exists some epsilon. Oh, sorry, I read the wrong one. We say that A is an open set if for every X in the element A, for every element X in set A, there's an interior point of A. For example, let's say because we said that X is interior point, right? Suppose the X is like this. Although it's this is a very abusive notation, but I want to try to show it using graphs. So, let's say A is like this. So what this means it's a set where the boundary point is not included. So it contains all sets in here. Let's suppose that. And you can see that even for any point you can find here, these are all interior points. Because for any point you can always find some ball that goes inside A. And for this, and everyone. And remember that I said usually boundary points are the points where it's not an interior point. But because we excluded the case where the boundary is not included in set A, we can kind of say that all the points inside A, they're all interior points. In this case, if all the elements inside set A is interior, then we say that the whole set is called open. So we say when set is open, we say it's those kind of sets. And in real number, these usually when we say open, you might have heard of a term like open interval. In Korean, it's 그 개구간이라고 하죠. Some sets you have some notation where it goes like this, right? So usually this is the interval where everything between 2 and 3 are included except 2 and 3, right? This is kind of analogous term for open set in a general term. So you can think of there being no 2 and 3 inside this set as being the boundary, right? Because in a horizontal, what you will see is that there's 2 and 3, and all elements are in here, but we're not including the boundaries, which is 2 and 3, which is similar situation to this one. And in this case, we can say that this set is open. So that's why we usually call these intervals open interval. It actually means it's open, literally. It's open interval, it's open set. And you can see why, because if you choose any point here, you can always get a small open ball. Although in this case, the open ball is an interval as well. It's the distance. So if you get any open interval, some epsilon that can go inside this set, right? So that's why we say those kind of sets are open interval, which in fact, in more general term, we call these sets open sets. These kind of sets are open. Okay, so let's move on from interior points and open set. And number 4 is a new definition, which we call some points as a limit point. So when there's a subset of a metric space, there are usually the points. One of the concepts you can find is that whether a point is an interior point or maybe the point is a limit point. So we're going to talk about what limit point is. Limit point is actually a little bit more intuitive, I think, because what this means is that I wrote some very long definition, so I'm just going to read it and then talk to you about what it means. So we define the point X as a limit point of set A. So if for every open ball centered at X, there exists exists at least one point in A that lies within this open ball. So what does this mean? So like, it's kind of related to, do you remember like the time we talked about like Q being dense? When we say like for any interval between two different numbers, there's always rational numbers. It's kind of related to this because it kind of shows that what this means, like basically it means like the set is kind of dense. So what this means that, let me just draw it again. Is it getting? Oh, and before we start, I'll write the attendance code for this session is 45. Okay. So the attendance code is 45. All right. Let's go. So again, we're going to have another subset A. We're going to have subset A, so it's going to go like this. Right? So there's a subset A. So what we're trying to do is that we're trying to show that some point is a limit point, and that is like, actually in this case, suppose there's like a point here. This is X. And let's suppose that we draw some kind of open ball like this, right? Then there's like a possibility there is some element of A inside here, right? I mean, it could be empty. Like maybe this part is like whole part is empty instead of X. But if we have an open ball, there's a chance that there could be some element inside it, right? And what we're saying is that when we say X is a limit point of A, that means like even if you draw like any kinds of open balls around X, there will always be some element other than X that is inside this open ball. So what this kind of means is like when I say dense, it's because something like this. So like X being a limit point, something like there's like so many points there is so many points near X, such that even if you draw if you draw a very small open ball, big open ball, any kind of open ball from X, there will always be some other point than X that is inside that open ball. Kind of means what it means to be like X is like a limit point, means like the set is dense. That's why we call that to be a limit point. Everyone okay so far, or any questions? Okay, so we call that to be a limit point. And we use this limit point concept to make a new definition, which is kind of obviously is closed set. Because we define open set, we now have to define a closed set now. And we say that A is a closed set if it contains every limit point of A. So what this means that, like I talked about how there's like a limit points, right? So in this case, X is a limit point of A, but there could be other limit points, right? And we say that if all the limit points of A is indeed the element of A, then we say that this set is closed. And this is because there are cases where sometimes a limit point of A is not really element of X. For example, like the very useful case you can remember is this. Remember we draw like a... Remember drawing set A like this? So in this case, the boundary is not included. But let's say like this set is very dense. Then what happens is that if there's like a point on the boundary, this is a limit point of A. Because if you make any kind of ball, it's going to interact some part of A. And because this is limit point, there's like a point inside here that's going to be element of A. So what this means is that this boundary point is a limit point of A, but this set is not closed because this limit point is not an element of A, right? Because this is not included. So these cases, we call these sets like they're not closed. But if they are all included like this, then we will call this set to be closed set, right? And analogous definition of closed set is, of course, closed interval. In Korean, that is called like pegugan. So you have something like this. Remember this? This is closed interval, right? And in calculus or basic calculus, we just kind of call them closed, not for a reason, but kind of looks close, right? It's like it looks close. But actually, when we speak, the reason we kind of say it's closed interval is because it's just like a special case of closed set. And the reason is because you can also see that 2 and 3 are limit points. Because for any small interval you can get from 2, it always has some sections here. So it will always intersect with the element inside here, which makes this 2 and 3 our limit point of this set. But because this is included now, we call this closed set. If it was like this, remember this one, open set? This set is not closed. So we talked about number 5. So we say that the set A is a closed set if it contains every limit point of A. So kind of an intuition means like a set that has all the boundaries inside. Although it's not always like that, but like in a more intuitive terms. And number 6, also we sometimes define neighborhood of X. Actually, it sounds more intuitive, right? But there's like actually there's like it's an abuse of notation because there are a lot of papers, like a lot of books, they define neighborhood of X as like a bit differently. So in this case, I'm just going to say we're going to define neighborhood of X to be any open set that contains X. So like if there's a point here, maybe X, and let's say this is some sort of open set that contains X. Probably because we're saying open set, it's like it's something inside bigger set, right? So if there's like a set, open set containing X, we call this like neighborhood of X. It's like, that's how we do it. That's why we sometimes call this like neighborhood of X, because like just like an open set that is containing elements near the element X. Let me see if I wrote some like some cautions. I didn't. Oh, okay. Before we do some exercises, I mean, we're not going to do it, but before I talk about some exercises, I want to emphasize on few points that you might mistake, you might not understand fully. The part is that the concept of open closed and the concept of open and closed and the concept of interior point and limit point kind of feels like as if they're like inverse concept, but they're not. What I mean is that there's like a famous like a pun or famous meme by topology mathematicians. They will say like the difference between door being open and closed and difference between a set being open and closed is that door is either open or closed, right? But set can be open or closed, or they can be both open and closed, and they can be neither open and closed. So let me tell you what this means. So basically, when we say like set A is open, this doesn't mean this is not closed. What this means is that if A is open, it could be also closed. And it could also be not closed, of course. And sideways also works, because like if A is closed, A could be also open. So both things could happen at the same time. Or both things could not happen at the same time. They could be like both open and closed, but they could be also both not open and not closed. So they're not like an inverse operation, because like if you say A is open, it doesn't mean that this is not closed, something like that. So just remember that this is not like inverse operations. So like for example, like example would be what sort of like this. So remember the intervals, like. Let's say there's some interval like this. I think this is an example. I'm not sure exactly, but I think like some people call this like Clopen set, or maybe this is not Clopen, but something like this. But this set, okay, this is like an exercise. Like, what do you think? Is this closed or open? 한번 손으로 해볼까요? 일단 그 오픈 셋이라 생각하는 사람 손 들어보세요. 없고 그러면은 클로즈 셋이다. 그러면 둘 다다. 둘 다는 없겠죠? 하나씩 했으니까. 둘 다 아니다. 역시 좀 아는 분들이 있네요. 둘 다 아닙니다. They're not. The answer is like they're not. They're neither open nor closed. You can use the definition to show this because, as I told you, if boundaries included, it can't be open because for this point, if you get some interval, it's going to always go outside the set, right? That shows that this point is not interior point. So there's some point that's not interior. So this is not open. But it's not also, doesn't mean this is closed. It's also not closed because 3 is not included, right? 3 has to be included to make closed set here. So I'm just giving you an example to show that the concept of open and closed, they're not like inverse operation. You have to think of it like separately. Although there are some cases we're going to see where like if something is open, something's closed, but that's like other topic to talk about. At least to a sole set, we can't say something is, if it's open, we just can't say, oh, then it's not going to be closed. No, it's not. That's how it works. And unfortunately, same thing also goes for, unfortunately, limit point and interior point. So when you say something is an interior point, that doesn't mean it's not a limit point. For example, like another interval example, let's say we have this again. Just to make it more simple, let's have a 4 here. So it's 2 and 4 and 3. Let's think about the point 3. Is 3 interior point of this interval? 맞나요? interior point인가요? 3이? 맞죠? Yes, 3 is interior point. But does that mean 3 is not limit point? No, because 3 is also limit point, right? Because it's interior point because you can always find some sort of like small interval, right? That goes inside the set. But it also means this is also limit point in this case because for any open ball you draw from here, it's always intersecting these points, right? Which means that it is a limit point, right? So this is limit point and interior point, something like this. Although like number like 2, they can't be interior point, but this is limit point, right? So there are cases like this, but there's also cases like this. So what I'm trying to say is that they're not inverse processes, so don't mistake it as if they're like one-to-one concept where something works, something doesn't work. It's not like that. They're different concepts. Just be aware. Any questions? No? All right. So now we talk. We're not going to do this exercise. You can do it DIY. You can do it yourself. You can try check it out. Which is, you know, like from the name, you kind of guess that the open ball epsilon is open, right? It's in the name. So we define the epsilon open ball as that. And because it has a name open in it, we're pretty sure that it's going to be open, right? But the problem is we haven't proved it yet, right? We didn't prove that it's actually open, even though the name says it's open. And since names can be very misleading, try to prove that the epsilon open ball of X is actually open. And you can really do this. So try it. And after using it, you can make sure that the open balls are all open, right? And I'll just leave it as an exercise for you guys to do later on. So we're not going to solve it right now, but this very nice exercise to think about. Open ball is actually open. You can actually prove it. All right. I said just earlier that open and close are not inverse processes, but that does not mean they don't have anything related. There is some related things, which is this one. So I'm going to talk about some very interesting properties of openness and closeness. And the first one is that if A is a closed set, remember that we didn't say anything about A, but we can say that A complement is actually open. So what this means is that metric space, we say if A is open, what this shows us is that actually the points outside A, this set, right? They're closed. We can show this actually. And I wrote down the proof. And reason I wrote down the first proof and did not write down the second proof for corollary is because if you check the Rudin's PMA, corollary part already have a proof. So you can check it if you want to. So I just solved for the part where there's no solution in the book. Okay, so I did it backward. So let's prove that if A is a closed set, then the A complement is open, which is actually a very nice exercises. And it's fairly less difficult than some other exercises. So let's try it. So I wrote down the proof. So we always go by the definitions. Like when you're solving these kind of questions, always remember what you're trying to prove. So we're trying to prove that A complement is open, right? So what we have to do is just that for any point inside A complement, we have to show that this element is interior point. Then it's done, right? So we just pick one element, which is X, right? So let X be an element inside A complement. Wait a minute. I think there's something notation wrong there. It does not intersect A. Oh, no, sorry. I'm sorry. I kind of got confused. Okay, let X be an element of A complement. Then there should be some open ball of X that does not intersect A. Do you see why? Because by definition, we said A is a closed set, right? Which means that because A is closed, all of the elements of limit point is inside A. And because we said A is not inside the element, because we said that X is not an element of A, basically what we're saying is that X is not a limit point. Because X is not a limit point, we'll be able to get some open ball that does not intersect A, right? So, because if there's no such set, then X will become limit point, then it's a contradiction, right? So we can always find an open ball that does not intersect A. Thus, we show that X is an interior point of A complement, right? Then, since X was arbitrary point in A complement, we conclude that A complement is open, right? It's very, I think it's a very nice proof to get used to because these sort of proofs are very, I think it's very elementary process of proof that you'll be using to prove things. So let me just give you by more using the example. So in case some of you are confused. So what we try to prove is that, let's say there's like some big X metric space and there's like an A. And we're trying to prove that the set outside, which is A complement, we're trying to show that this is open, right? So we have to show that for any element we choose here, this is interior point. So we have to find that for any point here outside, there's some open ball that goes just inside here. And what we do is, as we did in the proof, we just get some arbitrary point, anything just outside A. And remember that because A is closed, it contains all the limit points. So we'll be able to find some open ball that does not intersect A. Otherwise, there's no such open ball. Then this means that X is actually limit point. Then that's a contradiction because we already said that all the limit points are going to be inside A. So we'll be able to find some open ball here. So we can find this. But this literally means that this is interior point for A complement, right? So we kind of showed that A complement is open using the concept of interior point. That's how the proof is done, right? And the corollary is also similar, but it's backward. So A is an open set, and we want to show that A complement is closed, right? So I'll also leave it as an exercise. But it also works very similar. So I'll give you like 5 minutes to try it and try to think about the question and try to use your logic to solve it if you can. 한번 5분 드릴 테니까 한번. 그래서 30분쯤 해서 그냥 뭐 답이 안 나오셨어도 그냥 한 분 정도만 제가 한번 해서. 팁을 드리면 이제 다 그렇지만 정의대로 그냥 가시면 됩니다. 정말로. 그냥 정의를 기억하셔서 정의대로 가면은 생각보다는 아주 그러진 않은데 이제 그게 정의를 안 가면 오히려 더 헷갈릴 수가 있어서 그냥 딱 그냥 클로즈드 정의와 오픈셋의 정의에 따라서 이제 진행하시면 한 분 정도 해서 가볍게 해보도록 하죠. Okay. Anyone want to volunteer? If someone volunteers, I'll buy that person a coffee after the class. So, anyone? Anyone? I mean, you don't have to be correct. You don't have to be correct. I mean, even if you didn't solve all the ways, fine. If you come up and kind of show your logic, I'll buy you coffee when the class ends today. And even if there's no volunteer, I'm going to pinpoint one person, but I'll still buy you coffee if I do for that person. So Anyone? If there's no one, I'll just pinpoint someone. No one. 오케이. 그러면 남자분 했었으니까 이번에는 그 두 번째 한번 풀어주세요. 근데 안 풀어도 괜찮아요. 네? 아 그래요? 그러면은 옆에 분은 괜찮으세요? 아 괜찮아요? 그러면은 한번 풀어보시죠. 이렇게. 아 안 돼요? 안 돼요? 혹시 풀어보신 분? 답이 안 나왔어도 괜찮아요. 진짜로. 중간에 가능성도. 해보실래요 그러면? 아유 진짜. 오케이. 그 펜 이게 잘 나오나? 한번 보시겠어요? 너무 잘하시는데요? 잘하신다. 아니 잘 풀어주셨어요. 그러니까 okay, so he's correct. So this is how he did it. So basically, because we're trying to show that the A complement is closed, so we're always doing the definition, right? We're all starting from the definition of closeness, which means the definition of closeness was that every limit point is in the set A complement, right? So we just have to show that. So what we do is that we just pick some arbitrary limit point, and if we can just show that that element is inside a complement, then the proof is done. So we're choosing the x, which is a limit point of a complement, and using contradiction, we're just supposing that actually x is element of a. Suppose that, and we can drive a contradiction, and if there is one, then we kind of show that x is an element of a complement, then the proof is done, right? So remember, note that because x is a limit point, what this means is that every open ball of x is going to intersect some point in a complement, basically. So that means that x cannot be a limit point of a, because what this means is that, so in a way, x is like some sort of boundary element, like, so it should be something like this, right? Like if this is a, what x is right now is similar to the situation where it's like here, right? So what is happening is that because x is a limit point, for every open ball, it's touching outside region, which is a complement, right? Then by definition, x cannot be an interior point. Because for x to be an interior point, there has to be some open ball that just goes inside A only, right? So that's why there's a contradiction. And because we drive the contradiction, we show that x is actually element of a complement, which show that because all of the limit points is going to be inside a complement, then a complement is closed, right? So that's how we solve this. So that's very nice. Okay, we're not going to solve this one, but I just wrote down sketch of proof here. So another interesting properties of openness and closeness, which is the theorem where suppose that P is like a limit point of a set E. Then every open ball of B contains infinitely many points of E, right? So what it's saying is that, let's use the example of a, let's say that E is like what we did for like this, the interval, then we have this. So it's like here, right? So, and in this case, suppose that P is a limit point. We just assume that, let's say P is 2, right? Then we know that P is a limit point here. So what this theorem tells us is that for any open ball, we draw for number 2. So for any open ball here, there's going to be infinitely many elements of this set in this open ball. And we have to show how that is really true. And I did say like left exercise, but if you see like the gray part, I wrote down the sketch of proof, which kind of shows how to solve it. So basically you can kind of think of a way, because if like suppose like proof by contradiction, suppose that P contains only finite points of B. Like maybe there's like a point here. Now let's use C. Let's use the case where the P is 3. And suppose that there's like a, maybe there's miraculously, there's like an open ball here, where if you draw it, only finite elements of this set is in this set. Like 1, 2, 3. Let's say there's only 3, right? Then what we can do is that if there are only like 3 elements, just make an epsilon more smaller. So like this. Then if you can do this, then this is no longer a limit point, because there's no point inside here, right? And if it's finite. So from this, you can kind of see in the sketch of proof that if the case where P, there's an open ball where P only contains finite points, we can always count them and then just get the smallest open ball that just doesn't have these finite number of elements inside this open ball, right? So that's kind of a way you prove it. And using the theorem, what follows obviously is a fact of a corollary here, which is that finite point set has low limit points, right? Because just like let's say if the set has only 3 points, just make open ball really small like this. There's no limit point there. For finite set, there's not going to be limit point. So that's why finite points has no limit points. I did put like trivial in the proof, but it's not that trivial. So just note that. So using the theorem above, the open ball points in the finite set cannot contain infinitely many points, which kind of means that it has no limit points, right? And here's like some pop quiz. In this case, is finite point set closed? 유한집합은 닫혀 있나요? Is finite point set closed? What do you think? Okay, I'll do a survey. So hands up if you think it's closed. Okay, 2 people. Hands up if you think it's not closed. Okay. 중의적입니까? 여튼, the answer is it's closed, because remember the definition of closed set. Closed set is that we say a set is closed if it contains all the limit points. But finite point doesn't have limit points at all, right? To start with. In this case, we kind of vacuously say that it's closed. That's why we call finite set to be closed. Like the similar ones that you might see sometimes in mathematics, it's not like exactly similar. Like sometimes you have to show that empty set, like you might have seen this, like empty set is like subset of all set, right? We say that. But when we're proving this, how we're going to prove this is kind of similar. Is that definition of a subset usually means that for any element inside, definition of A being a subset of B, we prove it like this. For any element in A, this goes to also B, right? We solve it like this. In this case, there's no element in the non-empty set. There's no element in empty set. So we say this is like factually true. Because the assumption itself is just false. Because there's just no element. So you might hear terms like something is like vacuously true or maybe trivially true, I'm not sure. But those means like literally those kind of stuff. Like the if part is like false, so whatever you say is going to be true. Okay, some interesting properties of openness again, and which is I just wrote down some very nice things you should remember, which is like this. Arbitrary union of open set is open. So what it means is that for open set, even if you keep on getting them together, unioning them for multiple times, it's always going to be open. So open sets, if you just gather them and just make a union out of it, it's going to be open, right? And for intersection, that only holds for finite collection. So for open sets, if you do finite intersections, it's going to be still open. But for infinite intersection, we're not sure. It might not be open, right? That's like very interesting intersection quality. And the closed set works backward, which means that arbitrary intersection of closed set is closed, which means like as much as you intersect closed sets, they're all going to be closed. However, in the union case, for closed sets, only finite union of closed sets is closed. And if you do it this multiple unions, like infinite unions, you don't know if it's going to be closed or not. So that's some very interesting quality. And lastly, some very quick notation of sets you might see, which is a closure of a set. So what is a closure? This also means, I wrote down the definition, but it's very simple. What it means is that, well, we already, again, have like the metric space X and subset A. Then we define the closure of a set A as A bar, upper bar, which is basically just union of A and A. I'm not sure how to call this, A dash, A prime, I don't know. But what this means is that A dash is the set of all limit points of A. So in a graph, it would be something like, for being more intuitive, it should be something like, remember, like there was an X. Not good. There's A and X, there's A. But remember that there was like a case where it's like dash, and this was the boundary point, which is a limit point in this case. So what this closure means is that it's basically, it's containing all of this and all the boundary points, which are limit points of A. So you're just making a union, and you call that, well, A closure. And intuitively, you can kind of think of, because it contains all the limit points, we get a very nice property, which is A closure is closed, right? It's going to be closed because it contains all the limit points, like by definition. And also, actually, these are also like theorems you have to like prove, but I'm not going to do that. It's like too much time. So another nice property is that A is closed if and only if A is A closure. So if A is closed, A is equal to the A closure. And if A is equal to the closure, then that means also A is closed. Some nice properties to remember. And the third one is a very nice property, but sometimes very hard to understand. But it's related to number 4. So just bear it with me. So the definition says that if A closure is a subset for every closed set that contains A, right? So what does this mean? It's like, that's why here's like a more intuitive understanding of the A closure. So like, so let's say there's like a A. I think there's like a bit of a. I think there's like a notation mistake. I think this should be A. I think. Oh, so there's like A, and there can be numerous closed set containing A, right? There could be some this is a closed set containing A. This is also containing A. Some other closed set containing A. And what A closure is intersection of all these closed sets. So basically, A closure is the smallest closed set that contains A. That's how you should remember. So A closure in a more intuitive definition is actually the smallest closed subset of X that contains the set A. So there's a typo. It's not E, it's A. Okay. All right. Any questions? Okay, then we'll have some 10 minutes break, and after that we'll start again.